this is a topic that we've talked about before. We've talked about how we would take the derivative of a parametric equation so that we can find the slope of a tangent line or an instantaneous rate of change in the coordinate plane. When we're talking about taking a derivative in the regular coordinate plane, the xy coordinate plane, to find the slope of a tangent line, we would find dy dx. And to do that, we use this formula here. We said dy dx is equal to dy dt over dx dt. Because x and y are both functions of t, so we can take the derivative of those with respect to t and then divide them to get dy dx, right? You guys remember that? Okay. What we're going to do today is we're going to talk about how we would take the second derivative. So we're going to talk later more about what the second derivative means, but we've started talking about higher order derivatives. So if we want to take a higher order derivative of this, the problem we're going to have here is that what we get when we do this, the derivative of y with respect to t and the derivative of x with respect to t, these are going to be functions of time. These are going to be functions of t. So our dy dx is going to have t's in it. It's not going to have x's and y's, but it's going to have t's. So when I take the derivative, I can really only take the derivative with respect to time. Does that make sense? So when I try to take the derivative of the derivative, I'm not going to be taking the derivative with respect to x, which is what I actually want to do, but I'm going to be taking the derivative with respect to time. So let's look at this here. What we want to find is the second derivative of y with respect to x. All right, and this is the way we write that second derivative. What we know right now is dy dx. We know how to find dy dx. You guys agree with that? But what we want to do is we want to differentiate this dy dx with respect to x again, so that we can take the second derivative. Again, the problem though is that this right here, this dy dx, is going to be in terms of t. So we know how to take the derivative of this with respect to time. We don't know how to take the derivative of this with respect to x because it's not in terms of x. One solution to that could be to convert it to x. If we could, we might be able to use the equation where we have x defined in terms of t, and we might be able to get x's in there instead of t. But there's an easier way to do it. What we're going to do is we're going to take this differential and manipulate it a little bit. Instead of d dx, we're going to take the derivative on top with respect to time. So we're going to take d dt over dx dt. And now if I take this dy dx and I put it up top with the derivative with respect to time, I can do this. I'm going to say this again. I'm treating these almost like they're numbers themselves, and these differentials aren't actually numbers. What I did here is not a proof of why this works. It is somewhat of an explanation. We can't always treat these differentials as numbers, but it actually works out that this is true. So if we take the derivative with respect to time of dy dx, that means that once we get dy dx, we take the derivative, which is in terms of time, and we take the derivative of that with respect to time. Then we divide by dx dt. That gives us this formula right here. This is the way it's typically written, in some way like this. So what this means on top, the y prime is what we got up here, but y prime is going to be written in terms of t. So we're going to take the derivative with respect to time of that derivative, that first derivative, and divide it by dx dt, and that's going to give us the second derivative.